Hello, my name is Carl Malamud. I'm Chief Technology Officer at the Center for American Progress. It's a think tank in Washington, D.C., and I'm a part of a group of volunteers that have been working on a document that we're here to tell you about, the Archimedes Palimpsest. I'd like to thank Dan Bloomberg, who's our host from Google, for inviting us in, and Vince Cerf, who's the one that originally gave us the invitation to do this. My role in this project is pretty simple. I'm going to be running the FTP server, and there's not really a lot of rocket science to that piece. And so I'm going to turn it over to three speakers from the team who are here to talk about the work. Dr. Will Noel is the curator at the Walters Museum in Baltimore, and he's the one that worries about old manuscripts and what they mean and how to work with them. Abigail Quant is also here from the Walters Museum, and she runs their conservation operation, and as you'll hear, this document took quite a bit of conservation. Following Will, we're going to hear from Roger Easton, who's a professor at Rochester and is heading up a lot of our imaging efforts. Bob Morton is also here from ConocoPhillips. He's one of the team of imaging experts from around the world that have been working on this project. And then Mike Toth is going to speak last, and he's the program manager. He's administered several very large imaging projects in the past, and he's volunteered his time to keep everything going and work with scientists from dozens of places around the world, and also specifically to worry about things like metadata and making sure that we're capturing the right information as we create these images. So, Will?
Thank you very much. Thank you, Google. It's a great pleasure to be here. I am the project director, and I have a rather extraordinary story to tell, if I can tell it, and I have about 20 minutes to tell it. There's a philosopher called A.N. Whitehead who very famously said that Western philosophy is nothing but a series of footnotes to Plato. I'm going to make the case very briefly that Western science is nothing but a series of footnotes to Archimedes. What do I mean by this? I mean that Archimedes was the guy who first got abstract mathematical problems and attached them to the physical world, so that you could just think entirely abstractly and find out something that was true about the physical external world. I'll give you a very simple example. How to find the center of gravity of a triangle. What you could do is hang a whole bunch of triangles from the ceiling and find out where the center of gravity is for each individual one. That's not how Archimedes went about it. He was sitting in Syracuse in the 3rd century BC, and he thought, how am I going to find the center of gravity of a triangle? Well, I'm going to draw a triangle in the sand. I'm going to call it A, B, and C. And I might guess that the center of gravity in a triangle is going to be on the median line, AD. But being Archimedes, I'm not going to do this simply. I'm going to make it complicated. I'm going to do an indirect proof. So what I'm going to prove to you is that it can't lie on the line AX, say at the point T. Okay, so let's say that the center of gravity in this triangle is at the point T, and I'm going to prove to you that it can't be. I'm going to divide this triangle into 4 individual triangles. So the sum of the center of gravity of these 4 individual triangles is going to be, this should be identical to the center of gravity of the big one, right? Now, being similar triangles, the center of gravity should be in roughly the same place as those respective triangles as the point T. So they should be for the blue triangle at the point K and the yellow triangle at the point L. Okay. Now, those other 2 triangles there, the center of gravity for those 2 is easy. It's going to be at the point M because it's a rectangle and it's right in the middle of the rectangle. K and L, the center of gravity of those 2 triangles should be at the point N. That's exactly halfway between the point K and the point L. So the center of gravity for the 4 triangles is going to be on the line somewhere right in the middle of MN. Okay? If you add all those triangles together, the center of gravity is going to be in the middle of the line MN. But you know it isn't, because it's going to be at the point T. Now, those 2 lines, the line running through MN and the line running through AT to X, are always going to be parallel. Whatever the shape of your triangle, they're always going to be parallel. They're never, ever going to intersect. They're never going to intersect. And while they don't intersect, of course, you can't have a center of gravity. The only place they'll intersect is actually on that median line. So you know that the center of gravity, you have proved it without even hanging a triangle from the ceiling, that the center of gravity is going to be on your median line. Now, the nice thing is, you haven't got a center of gravity yet, you just know it's on the median line. But of course, a triangle has 3 median lines, And they coincide at one point. So you know that the center of gravity of a triangle is going to be a third away along, actually, of any median line, which is going to be at that point. So if you're Archimedes, you know that you can, just through simply working it out entirely in your head, that you can find the center of gravity. So, you know, if you're an eminent historian, you might try and hang triangles from a ceiling any old how, but if you're Archimedes, you just think about it entirely abstractly, and before you know it, you've got triangles that balance perfectly on the ceiling. The application of abstract mathematics to the physical world is something that Archimedes was very, very good at. And measuring surfaces is something that he was very interested in. Now, measuring a rectilinear surface, however complicated it is incredibly easy. You just divide it up into right-angled triangles, and before you know it, it's incredibly easy to measure. But measure an incredibly simple thing like a sphere, and that's incredibly difficult. And what Archimedes did was to pack it with triangles. And he had a recipe for packing it with an infinite number of triangles. So that way, he can calculate curves. Now, if you can apply abstract mathematical models to the physical world, and if you can calculate curves, eventually you can send a rocket to the moon, which is why Archimedes is the most important scientist who ever lived. Okay. Everything we know about Archimedes came from two books. They're very boringly called Codices A and B. Just two books. That's how we know about all of Archimedes' treatises. In the Renaissance, Leonardo got hold of copies of these two books. And with it, he found equilibrium of planes, which is where Archimedes starts talking about triangles. And typical of the Renaissance, he picked up on the ancient mathematics and found the center of gravity for a tetrahedron. It's very, very clever to do this. You can calculate the center of gravity at the Pyramid of Cheops. But there was another manuscript, Codex C. And Codex C, Archimedes didn't know about. If he did know about it, he'd have known that Archimedes had 1,700 years earlier already calculated the center of gravity of a segment of an ellipse, and many more complicated curved solid objects besides. So he can calculate the center of gravity of even a cut through one of those eggs. This manuscript, Codex C, well, let me tell you about the fate of Codices A and B. Codex B was last heard of in the Papal Archive in Viterbo in 1311. Codex A fell off the back of a truck in 1546. Codex C was only discovered in 1906 by a guy called Johann Ludwig Heiberg in a monastery in Constantinople. And that's what it looks like. But the Archimedes text in this manuscript is not the Archimedes text that you can see running down like this. It's coming in two columns across the page the other way. Along like that. It's a palimpsest. It was made in the 10th century, but in the months shortly before April the 14th, 1229, someone needed to make a prayer book, and they didn't have any parchment. So they tore up the Archimedes manuscript, scraped off the text, cut up the pages, stacked them in a corner, rotated them 90 degrees, got some parchment from other manuscripts as well, wrote over it, scrubbed it very hard, wrote over it in a very black ink, and turned it into a prayer book. And it survived as a prayer book for approximately 777 years, until it was discovered in 1906. And that's what it looks like now. It was sold at auction on October the 29th, 1998. But when it was sold, an awful lot of things had happened to it between when it was discovered in 1906 and when it was sold in 1998. One of the most remarkable things that happened to it is that sometime after 1929, someone painted over the pages with gold ground icons. We know that this is after 1929. So what you're looking at is unique Archimedes text that was overwritten in 1229, and then someone after 1929 painted a painting on top of it. Fantastic. The other thing they did was they left it in the bottom of their garden for quite a long time, so it got very, very moldy. Now, I can't go into this in great detail, but medieval manuscripts are made of parchment. That's the stuff your shoes are made of. It's tough stuff. There are two things that can kill it, fire and water. This was left in a bucket. And that's the page as it was in 1906, and that's the page as it is now. And you can see a big hole, a hole in Archimedes' brain, right here. You don't get more written off than this manuscript. It's in a terrible state. It is the unique surviving copy of On Floating Bodies in the original Greek, it's the unique surviving copy of the Stomachion, and it's the unique surviving copy of the Method of Mechanical Theorems. It was read by Heiberg in 1906, but it wasn't read very well because he didn't have the modern technology that we have now. There it is. It was bought by an anonymous owner in 1998, sold for $2 million, and he gave it to me. Fantastic. I don't read Greek, I can't add. And I do know about manuscripts, and I am in a position to find some of the people that are going to help. But it was a major problem, and we've been working on it for 8 years now. And I'm going to talk to you a bit quickly about some of the things that we did. We had an article in the Washington Post, and we got lots of responses. You know, the grandson of Rasputin said his name could be found in the Archimedes Palimpsest if only we looked hard enough. Lots of kooky things. And then a nice email from Mike Toth, who's going to speak to us later, who said that he worked for the government and he had some kit that might be able to help. It's a privately owned book, so we can't use government equipment to help us. But Mike's had a great deal of experience in running imaging programs and that sort of thing, which of course I didn't. So he works for us as RB Toth Associates, and he's the brains behind an integrated program of imaging, scholarship, and conservation that I'm briefly going to talk about. Conservation, of course, is the most important part of this thing. The way the palimpsest was made, we had to take it apart. It's hard work taking it apart. The main reason it's hard work taking it apart is because there's now glue on the spine. Now, glue is put on spine of books quite a lot, but not in the Middle Ages. There are two bits of glue there. You can see at the top that it's white, and at the bottom it's black. The black stuff's all right for Abigail. That's called hide glue. It's made out of animal parts, and conservators like Abigail have been taking this apart for time immemorial. The trouble is the Elmer's wood glue on the top. The white stuff's Elmer's wood glue. It's tougher than the parchment support itself, and that's probably been put off on since 1970 by some nice people called the Établissement Malais in Paris. So it took 4 years to take apart the book. That's a rare action shot. Abigail started on the 3rd of April in the year 2000, finished on the 26th of November 2003. I bought her a bottle of champagne. It was a long job. Abigail is a great conservator of manuscripts, but boy, did she need to work hard on this book. That on the left is the first page of the book. It's on floating bodies that's never been read before. But you can see that it's in a really bad state, and how on earth are we going to read it? This is a typical Abigail story. You can see the Archimedes text running vertically, right? And what you're looking at is a detail of the gutter. So Abigail performs brain surgery. Okay, there's a before on the left, an after Abigail in the middle, and then a UV photograph, very low quality, low res JPEG that we sent to Reviel Netz, who's professor of ancient science at Stanford University. He circles the circle and he comes back and he says, this is the earliest symbol of a circle in the history of the Western mathematical tradition. Great. So I send it to the owner. I say, here it is. This isn't bad work, is it? And he sends back, here's $10,000. Go do the same thing again. That's on a good day, you know, but there are lots and lots of bad days. Abigail's basic job is to prepare the palimpsest for imaging. And my job is to, and that's the imaging stage. And these are my images. Bill Christens-Barry from APL, Keith Knox, who now works for the Boeing Corporation in Hawaii, lucky fellow, and Roger Easton, who's the professor of imaging science at the Chester Carlton Center for Imaging Science, and who's going to speak to you in a minute. And he's going to talk to you about the imaging. I'm just going to show you a product of the imaging. This is the Archimedes text running along here. And that's what it looks like after he's done it. It took a long time to get there, but those are the images that the scholars are like, and however ugly these images are, that's not the point. The point is that the scholars can read them. And we distribute them at the moment in hard drives, which is one of the reasons we're here. We're about to have a problem. Some of the results of our work. This is Reviel Netz, who's at Stanford. Method proposition 14 of the method is very important because Archimedes starts dealing with infinite numbers. This is a UV photograph. Reviel tries to read it. The Q to AQ is a question to Abigail Quant, asking if the tear in the parchment is possibly original. Because if it is, then Reviel doesn't have to try and find a letter to put in there when he's doing his transcription. That's the method proposition 14 page with RGB on the left and processed on the right. There's a detail. You can see how easy it is to read with a processed image and how difficult with normal. And this is a result. Dear Will, in a couple of months, the first intellectual fruits of our labor will be published together with a complete transcription of one crucial side of one page, most of which is unknown to modern science. I send you the final lines of the article as it stands in draft form. It's understated. It reads as follows. To sum up then, the new reading from Archimedes' Indivisibles proofs calls for some reconsideration of the position of Archimedes in some key areas of mathematics, notably the two related fields of calculus and of infinity. Very learned article, very obscure journal, read by 5 people because Natalie Chernetska isn't married. And published on the Sunday Times Color Supplement. Eureka, exclusive, it's just a few lines of scrawled Greek text, but new technology has identified the hand of Archimedes, and the results are rewriting history. One of the interesting things about this project is that on a very, very academic level, we are fundamentally transforming the landscape of Greek mathematics, but there's also a great popular component to what we do. Another example is the Stomachion. The Stomachion is which uniquely survives in this manuscript. And it was known as Archimedes' box in ancient history, and it's just a square, and it's divided into 14 bits. And we knew that Archimedes was playing some kind of game with these 14 bits, but we had no idea what it was. And together with our new reading from that page, which as you can see is dreadful, we found out what it was. Archimedes wasn't playing a game at all. He was calculating how many ways in which those bits of that square can be recombined and still make one square. And that makes it the earliest mathematical study in the history of combinatorics, which is important, I think, to what a lot of you guys do. The answer, anyone want to guess? 17,152. We all thought we were working for Archimedes, but those of you that were paying attention will have noted that I said that other manuscripts were also used to make the prayer book, and they'd never been read at all simply because they were so faint. And we thought just for the purposes of completion, we should study those ones too. This from Natalie Chernetska at Cambridge University. We have 5 pages in this book that belong to their speeches by an Athenian orator called Hyperides, who was a contemporary of Demosthenes and Aristotle from the 4th century BC. 77 speeches were written by him in antiquity. None of them survived the rather important transition from the roll to codex. That's the book form as we know it today. This is the only Hyperides text that's ever been found in a codex. We've added 30% to the surviving Hyperides corpus, so people are rather excited about that. This is Nigel Wilson. He's at Lincoln College, Oxford. Dear Will, excellent news. The hard drive and photos came safely this week. At first glance, there's no more Hyperides, but several leaves of the philosophical text, on which I read the name Aristotle clearly enough. Well, clearly for Nigel is not clearly for the rest of us, but I circled it on the image below, and you can just see it there, and there it is, you see. That's Aristotle. We now have 7 pages of an unknown commentary on Aristotle that must date from the 3rd century BC. Now, where I come from the world of medieval manuscripts, this is just utterly sensational. You know, there are quite a few palimpsests around. A very few of them are important. The Cicero's De Republica only survives in palimpsest form. But to have 3 unique texts, and we're hoping for a 4th from one book, is, you know, it makes this book the 8th wonder of the world. This is how the scholars read it at the moment, through hard drives and through copy. And until about 4 weeks ago, we were dealing with 4 scholars, because you only need about 4 scholars to read Archimedes' text. But with the Hyperides text and the Aristotle text, we have a major distribution problem, which is one of the reasons that we're here, because we have to address it very soon. Because with these new discoveries, we have scholars we're talking 100, 150 scholars who we want to work on this project. When they work together, they can come up with some pretty wonderful results. We have a website. I'm not going into it. We are working on other technologies to improve our pseudocolor processing, including shortwave multispectral imaging, which 4 years ago was very, very expensive, but now you can just use with LEDs. And our provisional results are encouraging. We're also doing optical character recognition, but I'm going to leave my part of the talk leaving you with the forgery problem, which is why we're here in California, because we have 2 weeks of imaging at the Stanford Linear Accelerator Center over the next couple of weeks. We've been going for 8 years. There are a lot of people involved in this project, and nearly all of them are on this screen. I'm going to hand over you to Roger Easton, who's the head of our optical imaging effort, and he's going to give you a brief summary of the techniques that we've been using and what we've learned along the way and how to image the manuscript. Thank you very much. Roger.
Thanks, Will. So as Will said, I've been working on the imaging team for the Archimedes for quite some time. In fact, we actually started working on it, Keith Knox, my colleague, and I, even before Will did, because we did some imaging for the auction catalog that was published in the August, September of '98, before the auction. But our original intent, and what we have been doing subsequently with significant modifications, as I'll show you, was to do multispectral imaging of the palimpsest. And the reason is because the two inks, the overwritten ink that came later and the original ink, are different colors. And the slide here shows images at a bunch of different wavelengths, which illustrates that. Both inks tend to get fainter as you go to longer wavelengths because the penetration depth of the light gets longer. But the Archimedes ink, that changes significantly more quickly. So we're going to try to take advantage of that. Here's one of our early graphs that we made in the summer of the year 2000 when we first started to image this for Will. And you can see there the prayer book text is the upper line, and it's significantly flatter than the lower line, which is the Archimedes text. Sorry, I got that backwards. The prayer book text is the lower line. The Archimedes text is significantly brighter in the red wavelengths, which is the reason why, the difference that we're going to take advantage of. So the original imaging plan was to take advantage of this, look at the image in 30 different wavelengths in the visible, and then do subsequent image processing to try to extract the Archimedes text, to literally segment it from the original text. And this is taking advantage of techniques that are well known. They've been done in environmental remote sensing for years. So we weren't actually doing too much that was very new when we did this. The camera we had at the time, and we still use on occasion, was just marginally capable to do this. It was a relatively small sensor, 1536 by 1024, so 1.5 megapixels. And these days, when you can go down to your neighborhood store and buy a 8 or even a 12 megapixel camera, this is relatively small potatoes. This was a monochrome camera. It was cooled, which allowed us to image more gray levels. We got 12 bits of data rather than the 8 or 10 that you get from most normal cameras. But because it was a monochrome sensor, to be able to get the spectral recognition, we had to put a color filter over the front of it, and we used a liquid crystal tunable filter, which again, at the time, was relatively new technology, but is much better known now, which allows you to literally tune an electrical knob and change the wavelength of transmission. And so this camera, which was about 25K when I bought it in 1999, you can get that same capability for considerably less money now. So we're going to use these techniques we derived from environmental remote sensing, where we assumed a linear mixing model. We assumed that the pixel values were linear combinations of the different constituents, and then we tried to extract that, undo that, by doing a unmixing model using a pseudo-inverse matrix, which is, again, relatively straightforward, simple stuff that many people here are probably snoozing right now because it's so obvious. So here's a diagram of what that model would be. We take the images in the different wavelengths, and what we're trying to do is construct the inverse of the matrix E, which is the matrix is describing how the combinations of constituents get matched into the different combinations of wavelengths at each pixel. One other little detail that we had to deal with was, of course, in real life, here we've got a multiplicative model where the different combinations actually are combined multiplicatively, and in the calculation we want to assume an additive combination, so we simply had to take the logarithm to do that. And then we went ahead and did a least square solution of the matrix, real straightforward stuff, Moore-Penrose pseudo-inverse, and then we could construct images of each constituent based on that. And this was the first images that we got doing this. We did this in our phase one imaging, which happened in the summer of the year 2000. And so the original appearance of this one leaf, 70V, is on the left, and then the channel that shows the Archimedes text is on the right, where the level of whiteness is associated with how much the algorithm recognized that text to be Archimedes. So if it's white, it says it is Archimedes. If it's black, it says it isn't. And if it's mid-gray, there's some mixture. And so there we felt we had actually solved the problem. So there's a magnified view of that. But it turns out that was not a successful result in the minds of the scholars. The images looked very good to us, the imagers, but it didn't look good to the scholars. And the other problem was it was a very time-intensive process, both collecting and processing the data, and part of that was we had to do custom stitching at the time. We didn't have an algorithm that we could use. But it turns out, even with the fact that there was significant improvements in the visibility of the text, which I think you can see in the center there. There's a diagram of Archimedes that if you look on the original page, my memory is you couldn't even recognize that it was there. But it turned out that the scholars didn't think so. So our reaction to the scholars' reaction was one of shame and shock. I mean, we figured we had the problem licked, but it turned out we didn't. But there were a couple of simple reasons why we hadn't done it for them. And one thing they really wanted was finer spatial resolution. And that was the problem, again, with that particular camera, being only 1.5 megapixels. We took the images of those leaves in 2 shots and then stitched them together. And so we only got images that were about 1.5 megapixels by 1,500 pixels by 2,000. And so it worked out to be about 8 pixels per millimeter, which is certainly sufficient if you're just trying to recognize the text. But when you're trying to extract text from other text, it turned out it wasn't. And again, we clearly also need a more efficient imaging and processing to be able to do this much more readily, because it took us virtually all summer to process those 5 leaves that we did in that original phase. So then we adopted the technique that was well known to scholars for many years to read palimpsest, which is to use ultraviolet fluorescence imaging, where you illuminate the page with an ultraviolet fluorescent light, and that makes the parchment glow. And that enhances the visibility of the text. And why is that? Well, it's because you get a double absorption. The ultraviolet light is absorbed by the ink going in, and then the visible fluorescence is absorbed by the ink coming out, and that double absorption gives you an enhancement in the contrast of the text and makes it much more readable. So this was something that we had known about, but we figured that with the technique that we had before, we didn't need the ultraviolet fluorescence. Turned out we were wrong. So we also went to a simpler digital camera, which gave us significantly better resolution. And again, compared to what you can get now, this is relatively small potatoes. But at the time we got it, it was the limit of technology. So we used a Kodak DCS 760, which is a digital camera based on a Nikon body single lens reflex. Kodak doesn't even sell it anymore. They don't have any comparable camera at this time. But it gave us 6 megapixels, 3K by 2K, and it did give us images that from 400 nanometers through the infrared. And again, we illuminate now pages with ultraviolet fluorescent light, but we look at the visible fluorescence, so the 400 nanometers is sufficient. The other point is, of course, this is a color camera. It gives you a color image. And again, technology is probably well known to everybody sitting in this room. You've got, over the 3K by 2K sensor, you've got green, red, and blue filters. So in fact, you have to do interpolation. So we wind up getting slightly poorer resolution than in fact you would have expected, perhaps. So the technique that we finally evolved into we image now the pages in 3 illuminations. So we use a xenon strobe that's strictly, we don't process that. That is just for the visible appearance. Then we use a low wattage tungsten light, which gives you a very reddish illumination. And I'll show you the reason for that in a second. And then we also illuminate with a long wave ultraviolet, which is where we get the enhanced visibility of the undertext. And with this camera, we set it up so we image 600 pixels per inch, or 25 pixels per millimeter, roughly. And that gives us an image size over the whole page of about 7,500 by 5,000 pixels. But so to do this, we have to image the page in sections. So we image it now in 10 sections to do the image of a bifolio, which is a double-page spread of the original, double-page spread of the Eucologa and a single-page spread of the original Archimedes. And then we have to digitally stitch those together. And again, technology has evolved quite a bit from when we first started to do this. Our stitching algorithm was pretty poor, but we've adapted to get a new and significantly better one. So here's an illustration of the enhancement of the undertext using the ultraviolet fluorescent. And the image on the right, the Archimedes text, is running vertically, and that's, of course, is the text we're interested in. So then, now we have these 3 color images. So in effect, we have 9 bands. The strobe RGB, the tungsten RGB, and the ultraviolet RGB, even though in the ultraviolet image there really is almost no signal at all in the red channel and the green channel. It's almost all in the blue. But then we wanted to come up with a simple method for doing the image processing, and this was sort of a mutual effort with my colleague Keith Knox and myself. And it was based on the observations that the tungsten red channel, the red channel of the light of the image viewed under tungsten, this reddish tungsten illumination, shows almost no evidence of the Archimedes text. And the reason is because the Archimedes text is reddish. So you illuminate something reddish on a neutral background with a red light, it will tend to disappear. Whereas the ultraviolet blue channel shows both writings for the reason that we've already mentioned. So we came up with this processing strategy where we would encode the spectral differences of those texts in color to create these pseudocolor images that Will already showed you a couple of examples of. And these images, as we all absolutely readily admit, are hideously ugly, but they are useful and they are quick and easy to generate. So here's the illustration of the steps. So the same leaf, this is 92V93R, and this is Archimedes on spiral lines. And you can see the diagram right there in the gutter. This is the page that we use for our reference. We image this every imaging session. But in the image on the left, that's the full color tungsten, where you can really see the Archimedes text is virtually invisible. Whereas the image on the right, it's actually pretty apparent, though certainly it's still overshadowed by the overtext. So then we just go to the separations, and there's the red channel of the tungsten on the left, and the Archimedes text is virtually gone. And the blue channel of the ultraviolet, the 2 texts are at least of comparable contrast. So then we have to go and process those, and this is using the software that Keith Knox wrote, what we call Archie. It's now Archie 1.1. Where we take the red channel and the red channel of tungsten and the blue channel of the ultraviolet and normalize them by using a moving window, and then we balance the mean and variance inside that window. So we get a significant enhancement of the contrast, and also it removes a lot of the shading variations that are apparent in many of the images. And Keith did this in a very efficient way, so it winds up being able to run in 15 seconds for a whole image rather than days. And so we now have it set up, rather than having to haul all the images back to Rochester, which is what we originally did, Keith sets up his Mac laptop and runs it in his hotel room in the evening. So we have the images by the next day. So then, how do we display these to the scholars? Well, we want to take advantage of the pseudocolor, the eye's ability to distinguish the text. So we put the blue channel in the green and blue channels of a pseudocolor image, and we put the tungsten red image in the red channel. And again, the Archimedes text is not visible, or almost not visible, in the tungsten red channel, so it shows up as bright, whereas it shows up as dark in the green and blue. And the overtext shows up as dark in all 3. So as a result, the overtext comes out neutral, and the undertext, the Archimedes text, comes out with a reddish tint. And that gives you a color cue. And so there's another example like the one Will showed you earlier, the visible appearance on the top and the pseudocolor on the bottom. And now you can do a comparison. The top is the visible appearance. The middle is the appearance using that multispectral segmentation with the pseudo-inverse. And then the bottom is the pseudocolor. And you certainly get similar kinds of visibility of the Archimedes text, but the advantage of the bottom one is you also see the overtext. And that allows the scholars to be able to tell if a character has a break in it. They can see if that break was caused by the overtext obscuring the original Archimedes writing, which in the middle image, we were more successful than we probably wanted to be, though we didn't know that at the time. We've been able to significantly make that overtext disappear into the background, and it becomes difficult for the scholar to tell if that break was caused by obscuration from the overtext. So in these pseudocolor images, both texts are visible, and this was the scholar's request. We get that reddish tint, and we assume, or we have found that this method is useful to recognize about 80% of the text. And so there is a large image of one of the sections, and there's the ultraviolet, and then there's the pseudocolor. So we went into production imaging. There's Abigail putting one of the pages. This was one of the pages with the forgery on the bottom into our system, which has a computer-controlled XY stage, so we can readily drive the page to the particular section that we want to image. And this setup actually holds both the Kodak camera and the earlier Census multispectral camera, so we can do both kinds of imaging in the same setup. And but even with that, the scholars tell us that some of the text is still not readable. It's either underneath the forgeries, which is why we're here, why we're up at the Stanford synchrotron, because we're trying to do X-ray fluorescence imaging, or it's been eaten by mold, or it's scorched. So we're now trying to figure out ways to image these difficult sections, and one of the ways Will already hinted at, we want to do a little more sophisticated multispectral with more wavelengths, or we're going to try this X-ray fluorescence. And here's our team of X-ray fluorescence imagers, Bob Morton on the left, who's sitting in the front row, and Gene Hall from Rutgers in the middle, and Uwe Bergman from the Stanford synchrotron up on the right. And again, it's because of Uwe that we're here. So in X-ray fluorescence, the technique here is very similar to regular fluorescence. You bring in an X-ray to an atom, and that X-ray kicks out an electron from one of the inner shells. And then by consequence, one of the electrons from one of the next couple of outer shells drops into that to fill a hole in the inner shell and emits a photon, an X-ray photon at a wavelength characteristic of the particular material. So this allows us to do spectroscopy on the inks at a particular point at the same time. So this was a test image that was actually done with a test system, not using the synchrotron. So this is one of the forgeries. And then in that particular section, do an average spectrum, and you can see a variety of X-ray peaks there, and those are characteristic of all the materials, including the iron. This ink is iron gall ink, and so it has traces of iron in it. And so that's what we're counting on using to try to recover that text. So here are a bunch of different images from using wavelengths characteristic of different materials to try to extract that. And if you look at the calcium image in the lower right, there's a lot of calcium present in this because that's how they treated the parchment. And there you can see the text through the paint. So our first test images, and Bob and Will spent quite a few sleepless nights putting these together last year. I fortunately had to teach, so I wasn't available to go and spend my nights working on this. But there's a small section, and there is an image using an EDAX system, which is a commercial system. And one of the interesting things about it is you can see both writings on both sides in the same image. And here's an illustration of trying to indicate that a little more clearly. The face, the page 163 verso on the left, and then 163 recto, the back side of it on the right, but it's been digitally flipped to give you the mirror image, and you can see that those writings, you can match the writings in the EDAX image in the middle with the different writings on the different sides in the same image. So again, we've mentioned it a few times. That's the reason why we're here. We're at the Stanford Synchrotron Radiation Lab just up the road, and taking advantage of that. And here's one of the pages in the setup. This was when we did the first tests of this last year. And so the X-rays come in through that tube on the right and then are measured by the sensors both behind and at the bottom, and use those signals to try to recover the different wavelengths. And so here's the first examples of writings from that. And again, I didn't have the pleasure of being here, but that image on the right took how many days to put together? 30 hours to put together. So now I will turn it, that's the imaging section. So now I'm going to turn it over to Mike Toth, who's going to tell you a little more about what the management and some of the data issues have been.
Heck with it. As both Roger and Will have noted, we've got a good team here, and we've got a good process in place, starting with the conservation and the imaging, and working our way through to ultimately gaining knowledge about the Archimedes. And now is a point where you all come in, and we're particularly interested in your thoughts on this, because we're looking at the data. And we've been looking at the data throughout this process, but we've been working with a closed system. We've had a given set of scholars. We've had a given set of image processors. Now we want to make this more broadly available for people who may want to try different imaging techniques, who may see different things in the Greek text, and they want to get back to these original images. So the question for us is, how do we make these original images available to a broader audience in wherever they may be around the world? Now, early on, as we said, hey, we're going to collect large amounts of data here, we created a metadata standard. Part of that's basic Dublin core. Basically, what is it? Intellectual property rights, all the images are copyright, the owner of the Archimedes Palimpsest. We have a range of information there. But one range of information that I think is truly unique for manuscript imaging is the spatial information. Because when we looked at this, we said, hey, this is the equivalent of having a satellite over the globe, and we're looking at coordinates on this globe. In fact, just the other day, as we're looking at the XRF, we're saying, well, we're going to be imaging from the back. Which way is our world going to spin? What's 90 degrees and what's 270 degrees? So we're trying to address all these. We're trying to create a standard here. So part of this was creating a standard for our imaging so that you could go back to those original images on our coordinate system and pick any point in this coordinate system. And we, back in 2000 when we were starting this, we went back to the content standard for digital geospatial metadata, extensions for remote sensing metadata, following with our analogy to the satellite over the Earth. And so we created this where we have an X position, a Y position, and various coordinates there. So we have a spatial capability here. Now, does this help Google? How would Google work with this? You've got Google Maps. You can search for Archimedes, and you can look all around the US, and people can do mashups and find locations on Google Maps. You also have Google Books. We have Reviel Netz's book there, the works of Archimedes, translation and commentary. We have Heath's early translation, the works of Archimedes, which actually use the Hyperides. Now, how do we bring those together is our question. And can we use the same type of method, the same methodology that you're using for Google Maps? Can we do this on a scriptospatial scale, if you will, instead of a geospatial scale? Can we apply this to our manuscript? Is there one question for us is there enough information there? And then the question for you is, how can you use that information? How can you make this available to scholars who are saying, okay, I want to know where the word, whatever that word is, the starting with the epsilon there, or Reviel's input, or Nigel's comment. Can I find those? Now, it's pretty straightforward as we go through the various images here, the UV and the natural light and then the pseudocolor. Bigger challenge is when we get to the XRF. We've got registration issues here. We've got to address those, and we spent, I think, all of a full day, an afternoon and a full morning, trying to make sure we've got the metadata squared away for our upcoming XRF imaging session, so that ultimately you can correlate this information with the visual information here. That's fairly straightforward. Now the real question is the transcriptions. This is a transcription by RevealNet of that same page that we were looking at earlier. And these are the same points that I pointed out earlier. And the real challenge for us is going to be to bring it back to the original image. We frequently, you will see transcriptions or translations in books. And in Google Books or whatever it may be, you'll relate to those. But how do you get back to that original image? And that's what the academics want to look at. Or a processor who says, hey, I think I've got Archie 3.7. Let me try to crank this through these images. Okay, how can I apply the same type of thought to the original image, not just to the transcription, not just to the translation? And how can I relate these together? How can I relate it to references in various books? Can I relate that to the specific image? Can I go back to that thought on sphere and cylinder or whatever in the original image there from a book? Can I do it from a transcription and relate my notes to that if I have the word maston, for example, I can find that in the original note. If I have the word enenthoi, can I put that into the book? And so can we relate it to the information in an index, for example? This is RevealNet's book. Can I relate back to those original images? And that's our question for you really is, do we have enough information here? How do we make our data available? There's going to be distribution questions on the data. I mean, I just got a terabyte of Archimedes data at home very quickly. The FedEx box arrived, sat on my front doorstep, and there's that information with the hard drives in it. But we're going to have to move this around by internet, and we're going to have to move around good quality images there. So our plan currently is to make the data available sometime this year. We're going to make it available in a very simple, flat file. We're going to use our metadata standard, and we want this available to the broadest range possible of students, scholars, educators, and the general public. So this is getting beyond our narrow circle of the scholars, the imagers, the image scientists. And we want them to be able to link to the information they need, to be able to search across the original images, not just the transcription, not just the notes, not just the books. And then we're going to make this available to anyone, including Google. And what do you do with it? What type of GUI do you develop for? What front end goes on this? So that's the kind of a heads up here as to what's going to be coming, and then what do you do with it? And who is it good? What is it good for? There's more than just this. I do not believe the others, any of the other imaging projects, currently capture the spatial information. But there are a number of other projects: the Herculaneum papyri, the Oxyrhynchus papyri, Codex Sinaiticus. That effort's just starting up with the British Library, International Dunhuang Project. Also with the British Library. All of them are collecting large amounts of images, large amounts of metadata. How do we standardize across this? And it may be an organization such as Google that gives us the impetus to standardize across our various efforts. So the question for you is, what are your thoughts on this? I kind of got skewed over to the right there, or the left there. What are your thoughts with regard to what we're doing? What are your thoughts in terms of making this available? What are your thoughts with regard to how do we make these images available to the broadest group possible and make it available for them to work with it as they need to, or as they can make it available to others? So there's a question back here.
Saying, go back to the original image, and which one?
That's a good question. What we've said is that right now the TIFF image, we have different versions of images really. We have the original, what is that, a 12-bit or 16-bit TIFF, okay, and then we have the processed images. And those are all TIFF images. We then push around JPEGs, but those are not our standard images. We want to make those available in ASCII so that you're not dependent on any other standard. We're doing the same with the X-ray fluorescence, where we're going with the ASCII. We're then converting those into TIFF. So the original image as shot by the imagers, which are the 10 images per page, and then the TIFF image of each page. Question in the back?
Can you repeat the questions for us in the back?
Okay. The question was, which are the original images? And that's what I was saying. It's that TIFF, and then we're going to make those into ASCII images as well. Other questions or comments for any of us here? How would you use this? You just host it on Google Books as a book, or do you use it on Google Maps or Google Archie, or what do you do? We welcome your thoughts on it.
You mentioned that the manuscript was copyright of the owner of the manuscript. I gather from what you're saying now that he's not restricting distribution of it in any way.
He's protectively copywriting it so that someone else cannot claim the intellectual property from that. That he wants to make it available, but so that no one else can claim it proprietarily for their organization or for themselves. He does not want this to become a Dead Sea Scrolls, where these scholars held on for 50 years to these scrolls. He wants to make it available, and that's why we're here, really, because he feels that you offer opportunity for us to make this available. We welcome your comments. You can question them.
One suggestion, if you're going to be distributing the files directly, is to look at the peer-to-peer solutions, like especially BitTorrent might lend itself to large file distribution in a distributed way that's more scalable than perhaps just downloading it straight from the server.
Okay, I appreciate it. And the problem there is that would work well for pushing it around amongst our peer group. But there's others, this has really developed as a project as people who have gained insight into it, like you all, and who then say, hey, I think I can help. Now, many people come up, oh, well, it's easy, it's obvious. I can just use Photoshop, and they then find it's more complex. But all the people here who are working on this project have gotten some visibility into it and then said, hey, I can help. The question was with regard to peer-to-peer networks and use of peer-to-peer networks. And that's where we want to make this more broadly available so that people who may not be as part of this peer group can access it. And there are a lot of people out there, both imaging scientists and mathematicians, who are very interested in this, and give them opportunity. They've had no insight into this or limited insight. Give them the full information. Allow them to work with that in any way they want to.
You don't necessarily have to distribute your entire data set to everybody. It seems to me that representative samples would be useful for people that just want to play around with it.
So you make the statement was representative samples alone would be useful for people to play around with, and.
Somebody has an imaging idea that they want to try out. They don't need your entire data set. They'll try it out on one or two sample pieces, and if that works, then maybe they'd contact you to get the whole thing.
And then we go peer-to-peer and send them. Okay, that's a good point.
Yeah, and with respect to copyright and distribution, you may wish to look into the Creative Commons or other similar licenses that allow you to retain some measure of control, still allowing for public use within certain areas.
Okay, we'll have to take that up with the owner, and how does that restrict you or enhance?
That's a good suggestion. Basically, we're looking at a Berkeley-style license, which is you can do whatever the hell you want with it. Please don't sue us. In terms of distribution, we're just starting. We'll put a terabyte of disk up in a colo, BitTorrent, HTTP, FTP, you name it, and the core underlying strategy is massive replication of either small parts or large parts. So naming the files using an ISBN number and then identifying, where within the document you are, so that you have at least some ability to self-identify these things. The hard part, though, is once the data is out there, how do people start building the GUIs and that the scholars want? How do people begin applying the different imaging technologies and feeding those results back in? Because we hope that in addition to our core images, there's going to be additional images generated by other people that look at this and say, well, I've got some DSP algorithms I can add to this and recover even more of the text.
So the metadata that you were talking about, I don't know anything about it, but does that provide an absolute coordinate system so that two people anywhere can talk about, that word?
Yes, it does. In fact, the question is, does the metadata provide an absolute coordinate system? And yes, we have the absolute coordinate system and then the offset, because the leaves are mounted, so there's some offset there. And where is 0, 0? Where is our prime meridian and our equator? So we define that in terms of the bounding coordinates, and then you can work across that. You look like that didn't quite answer? Okay.
Are some of the translations already available, the new translations?
The RevealNet. The question is, are some of the translations already available? RevealNet has published Sphere and Cylinder 1 with Cambridge University Press, and Sphere and Cylinder was already in codices A and B, but one of the things that I didn't say is that the Palimpsest is also the unique source of the diagrams that Archimedes drew, and that's really important because mathematicians think in diagrams, they don't think in text. And so the diagrams in the Palimpsest are very, very important for that edition. Heath's translation isn't really a translation at all. It's a modern interpretation of what Archimedes was saying. So actually Archimedes is a truly foundational figure in the history of Western philosophy and science that has never been translated into English before. There are, in those learned articles that I was showing you, there aren't translations, but there are expositions of the things that we found, and the journal was Sciamus, for those that are interested, volumes 1, 3, and 5, actually. And we want to make this available as quickly as possible. So, we're hoping for transcriptions. We've now got a transcription of the whole of Codex C, the whole of the original Archimedes text, except for the forgeries. And that will be completed by the end of the year. And we're hoping to have it up on a website together with the images upon which those transcriptions were based. And this is a very important point because, of course, when you're thinking about what the original images are, you're not working from a manuscript, you're working from processed photographs, which are man-made things, and sometimes you're having to go back to the photographs that Heiberg made in 1906 because they're now the only source for the images. So it's a rather complicated set of data to put together. And the other thing is that in any edited text, there's always an awful lot of guesswork. So, as you know, there's a lot of editing to be done. Yeah.
Why do you call those paintings forgeries?
Why do I call them forgeries? Because they're trying to look Byzantine. They're trying to look like they're 12th century. And we know that they were done after 1929 because they're copied on a 1-to-1 scale from Henri Aumond's Manuscrit grec de la Bibliothèque Nationale, which is an album of pictures taken from Byzantine manuscripts, but at a reduced scale. But Abigail measured them, and they copied from it. We've also done some pigment analysis, and there's a particular type of green that only became commercially available in Germany in 1938. So we actually know that they were done after 1938. That's why they're forgeries. The interesting question is, why don't we take them off? And there are two reasons. One is that we might damage the text while we're trying to take them off. And the other reason is that even if we haven't got the technology to read under them now, and as you can see, we're beginning to get there. In 50 years' time, someone can have another crack with more modern technology, and at least we haven't destroyed the book. You know, one of the things about palimpsest is that in the 19th and early 20th century, people, to try and read the text, they used to put all sorts of acidic paints on them, really, to paint them over with iron gall or with a gallic ink or even with hydrochloric acid, which would temporarily make the undertext more visible, but in the long term destroyed the book. And we can be very grateful that Heiberg didn't actually do that, because then we'd be in even deeper trouble. Yeah.
With the scholars, if there was a nice GUI, if there was a nice, streaming data, draggable interface, would the scholars use that, or would they just print it out?
Oh, that's a good question. The question was, would the scholars actually use a really nice streaming interface, or would they just print it out? And our imagers tried very, very hard to make very, very wonderful pictures, and Nigel Wilson is a scholar of 60, and he does his transcriptions in the summer month using a magnifying glass from a printout. But other of the scholars are very, very computer literate, and they do use the hard drive. Now, our interface that we've developed so far is effective but clunky, very clunky, and they would love a better interface.
Last question. We got the high sign here on time.
Okay, so why not use PNG for the images? Because it's lossless, works in all the browsers, and then maybe have some JavaScript on top of that to let you see what the translations or possible translations are over it.
In PNG, Carl, you want to?
Question was, first of all, why not use PNG instead of TIFF? Well, that's a no-brainer. We just happen to, TIFF is how we capture, and transcoding to PNG is easy. Second part of the question is, why not build some JavaScript, pull up the PNGs, lay the text on top, and that's the great beginnings of a user interface. And I'd love to talk to you more about it. Yeah. Well, one of the things we're trying to focus on here is we think there's going to be lots of UIs out there, different ways of people working with this data and similar data. And so part of what we're focusing on is making sure we got the metadata right, the transmission method, we're getting this stuff on the net nice and solid. And so rather than spend all our time doing, Ruby on Rails sitting on top of a MySQL database that does this and that, we think a lot of people will do that level. And kind of our prime mission is making sure that we get the core data out there, but we're also very interested in how to build the UIs on top.
There's one other, as far as the actual image, whether it's PNG or TIFF or JPEG, one of our key considerations is the archival availability of this information. It's got to be available 1,000 years hence, however many years hence. It's a very fragile object. We don't know what its future may be. This may be the only history of the object, and we've got to preserve that for future generations. Why we're actually going back to the basic ASCII with basic flat file there, so that anyone in future can put it into whatever they want. They don't have to worry about whatever version of the software it may be, and so that it'll be available for generations hence. So I'm told that this ends the formal discussion, but we're available for another half hour if you want to chat informally. So thank you very much.